Hello everyone and welcome to this tutorial of non-terrestrial networks deployment. In today's tutorial, we'll be having a step-by-step guide on how to deploy non-terrestrial networks on, let's say, your local VM. And along with that, we will also be touching the what part of NTN to exactly understand the deployment process and configurations that we are going to use in the video later. So before going with the deployment part, let's quickly have a look on what NTN exactly is. So this is just a quick Google search on non-terrestrial networks, and the very basic definition uh, is that it's a communication system that use space-borne or airborne assets like satellites or HGPS to provide connectivity uh, in addition to or instead of traditional ground-based cell towers. So these ground-based cell towers, they basically refer to the terrestrial networks, which basically use the ground infra like cell sites, G node Bs, the optical fibers, Wi-Fi's, and all those things. So all these generational networks like 2G, 3G, 4G, 5G, 6G, and so on are a part of terrestrial networks itself. So this non-terrestrial network basically uses the satellites in order to accomplish the end-to-end connectivity from the UE to the core network itself. So if we want to have a look on the architectural diagram of NTN, then this one is very simple. If I zoom in, now here you can see on the leftmost side we have the UE itself, right? And as we move towards the right hand side, then there is a airborne platform. It could be spaceborne platform as well. So this means basically the satellite or anything which is in the air itself, right? So between the UE and the satellite, there is a link called service link, which is basically used to represent the NRUU data from the UE to the satellite. And from satellite, there is a link called as federal link to the gateway itself. So this is the satellite gateway, which can be present on the ground. So this federal link is basically used to forward this NRUU interface messages and to handle all that uplink and downlink parts that is received from the UE to the core network or the G node B itself. So this is a pretty simple diagram of this non-terrestrial setup. Now, if we wanna have a look on to the main satellite architecture itself, then let me quickly share one more diagram with you if I can find it. Okay. Oh yeah, this one is also a very good diagram to understand different type of non-terrestrial networks. So these non-terrestrial networks are also divided on the basis of altitudes. So as you can see here, we have the ground level where all the terrestrial network things happen, and if we go above, at different ranges we have different type of terrestrial networks. For example, at 150 meter we have the UAV type of NTNs, which includes drone. Then if we move a bit upward, then we have this airbornes, right? Then if we also move a bit more up, then you can see the satellite, which is on the top, right? So this is how the NTNs are divided based on the orbits. Like you must have heard about LEO, GEO, MEO, and all those orbits. And yeah, this is also a very simple architecture of NTN where we have the UE on the rightmost side, which is connected to the NTN payload. You can consider it as a satellite, and this is connected via the satellite link, and we have the NRUU interface over here. And also the satellite is connected to the ground via the gateway via this federal link itself. And then this gateway and G node B are connected to the 5G core. And yeah, this is the one I'm talking about. Okay, so if you have a look here, now we have zoomed in the G node B itself a little bit. So here, if you will see, we have the NTN payload mainly and the NTN gateway as well. So these two basically represent the NTN service link provisioning system, right? And then also we have this NTN control function, and on the right side we have the G node B functions, which are basically on the ground. So this is the overall, how the non-terrestrial architecture looks like. We have the UE, we have the 5G core, and in between we have the G node B. So you can consider like we have the service link over here as well and the federal link over here as well. And uh, and like you can consider the whole this payload plus federal link plus gateway plus g node b as a satellite access node instead of g node b itself. So you, if you see this whole g node b part along with the dotted area, you can consider this as a no satellite access node, which in terrestrial network we call as g node b. This is somehow similar. And yeah, also if we if you go on this 3GPP page as well, then this set non-terrestrial networks are two modes, or based on payload they are divided basically. So the first one is the non-generative payload mode, or we call it bent pipe payload. Also we call it transparent mode as well. So all of these things refer to the same thing. So in this, if you have a look on the diagram, on the left side we have the transparent payload non-terrestrial networks, which basically represent the G node B on the ground. I mean, the 5G RAN is on the ground connected to the satellite gateway, and the gateway is connected to the satellite itself, which is present in the sky, right? So the main difference between both of them is that in transparent mode, the RAN part is handled on the ground itself, whereas in the regenerative payload, the RAN part is shifted to the satellite itself. So it's on board processor, right? Now your satellite can perform all the RAN operations, like all those MAC, RLC, PDCP, all those layer work can be done by the satellite itself. So the RAN is integrated on board with the satellite here. And also, like, it's not like the whole RAN needs to be a part of it. There are a lot of different types where you can disaggregate the RAN as well, where your RU can only be present on the satellite and your CU and DU will be on the ground itself. And there is one more disaggregation where your RU and DU will be a part of the satellite and your CU will be based on the ground. So there are different approaches, and I guess ORAN is also working on a lot of things. So yeah, this is like an overall idea what NTN exactly looks like, their architectural diagram and all those things. Now we can, there was just one more diagram, yeah, this one. So these are the classes of orbits on which the NTN is also categorized. So we have LEO, which is least far away from the Earth surface. Then we have MEO and GEO. GEO is the like the satellite in GEO are stationary with respect to Earth, right? But in case of LEO, satellites move very rapidly because they are in a low Earth orbit, and you can also see the distance from Earth surface of all these orbits. Now, this is all about the basic introduction about what NTN is and all those things. Now let's move back quickly to the deployment part. So for the deployment, we are using OpenAirInterface, which provides its own documentation on how to run a non-terrestrial networks. So we'll be following this all the way, and yeah, let's get started with the deployment part. So yeah, obviously this time we'll be using the RF simulator, because if you want to perform this test in real world scenario, you will be needing this NTN channel emulator and SDR boards as well. So as we are using the RF simulator, we need to simulate some packets to act like the whole scenario is working with a satellite, right? So to perform a simple simulation of satellite in the geo mode, we need to add these parameters. So what this means is, like, we are adding some propagation delay, because when we talk about non-terrestrial networks, there are several factors that we need to consider. For example, the distance between the UE and the satellite is very much, so due to which there is a propagation delay when the packet reach to the UE from the satellite itself, and vice versa. So we need to simulate that packet as well, because now we are using the simulator, and we need to tell the simulator, okay, you need to put this much of delay so that it can act like the packets are coming from a satellite. So in case of Geo, the delay is pretty much high. For Geo, we need to add this as a command line parameter for both the G node B and the UE to add a propagation delay. And for the simulation in the LEO orbit, we have two channel modes, right? The first one is the transparent and the second one is the regenerative. So both have their own use cases, and in order to specify which mode you want to use, we have this configuration where you can specify the trans and regenerative mode here itself. So this configuration file is available here. We need not to modify this. It basically contains the normal information. We have two blocks. The above one is for the G0B and the below one is for the UE, with the type as transparent mode, and some noise is also added. Now we have some additional information. If you want to run the Leo mode, then you need to add this option in the config file itself. Otherwise, you can also give it as a command line parameter while running the G0B and UE commands. So moving further on the G0B side, so here are some parameters which we need to know before configuring them. For example, here we have the sync validity duration. It's a timer in seconds basically that tells the UE, okay, like how long it can use the NTN information from the SIB19 before it must require new data. And then we have this cell specific K offset value, which is it sets a scheduling offset specific to intent to align like certain procedures or resources. And then we have these TA common and common drift as a parameter, which are like timing advance parameters. The base value is in fine units that represent the propagation delay between the G0B and the satellite. Then we have some position and velocity variables which are provided over here. These are for the XYZ coordinates of satellite position. Same for velocity. Now you can configure all these parameters in the configuration file, as you can see here, both for the GEO satellites and the LEO satellites. Now we have some timers parameters over here, which are also necessary. And there is also one more important thing that when we talk about NTN, the very big challenge here is the throughput and latency things, right? Because latency is pretty high as compared to terrestrial networks in case of non-terrestrials. So in order to improve the throughput, what we usually do, what we can do in case of NTN is like there is a feature called as disable HARQ, right? So we need to use this feature, disable HARQ. So this will basically help us to increase the uplink and downlink throughput. So please make sure that you are using the UE which supports release 17 features, right? Otherwise, this feature will not work. And to enable this feature, we simply need to use this value. And the configuration file is already available here. So if we go a bit down, and these are similar things. We want to simulate the packets in the LEO satellite. You need to include this and then run this command. And for the GEO satellites, we need to go to CMake targets and then run this command. So so at the UE side, we only need to configure a few parameters because you receive most of the parameters from the G0B itself via the SIB19 interface. So there are some position parameters, and here is a sample command to run on the UE with the following configuration. This one is for the GEO satellites, and for LEO we have some additional parameters, and this command is for LEO where we have some additional parameters added at the end of the command. And for the GEO we have this command that we need to use. Okay, so let's move to the terminal part for testing this overall setup, right? So this is my terminal, where on the left hand side I will be configuring the G0B and running it, and for the UE we'll be using this right hand side terminal. In my case, I've already built the OpenAirInterface, so I will start directly with the commands. So for the G0B, let's say if you want to deploy in the geo mode, here for the geo mode the command is this one, which you need to run by going in this specific folder. So let's copy this command, and also like for the UE and the G0B, and if you want to run the G0B for the geo scenario, what you need to do is you need to add this command line parameter as well. So let's add this parameter after this command, and now we can run our G0B. So now it's creating some void samples, and now the G0B is running. If we go a little bit up, we can see the configuration we have used. For example, this is the command we are using, and these are the timing parameters that we have already discussed in that readme file itself. And if we go a bit down, then here we have the RX and TX, the number of antennas, and here we have the downlink frequency, the uplink frequency, and the band we are using here is 254, right? Also, here we have, here we have the ng setup request and response messages, and you can see in this line now the AMF is associated with the G0B itself. Also, we have some F1 AP messages exchanged between the CU and the DU, and these PLMN and all these parameters also. And these are some file layer configurations which are taken from the configuration file itself we are using to run the G0B. So you can also have a look on these parameters. And now we can start our UE. So for the UE, let's go a bit down. Yeah, in this section for the geo mod, we have the sample command which we need to run, and here the RF simulator propagation delay is already added, so we simply need to run it, and yeah, we are good to go. The UE and G0B both are connected. We can also have a look on the messages exchanged between the G0B and the UE. So here you can see the connection begins with the random access procedure here, right? And now these message 1 to 4 where the UE initiates communication, and then UE pushes this RRC connection request, right? So now you can see the acknowledgement of message 4 as well. And if we go a bit down, we have the selection of PLMN, and the UE context is created. And now the PDU session is established and peers are configured. The network performs this RRC reconfiguration to finalize the connection parameters, right? So we can also see the LCID4 and all these messages. So you can track like each stage in the logs by noting the sequence of RRC and gap, uplink, downlink information transfers, along with key matrices like BLER for radio link performance and everything. And we can also have a look on the logs of AMF. So here you can see the G0B information, the status is connected, and the UE is also registered, and we can perform an end-to-end connectivity test by pinging the CN 5G core from our UE. We have this interface, we'll be using this for the ping test. And you can see the ping is also successful. So yeah, that concludes the step-by-step tutorial of the UE connection and signaling with the G0B in this whole end-to-end deployment scenario using the OpenAirInterface. Thank you for following along, and see you later.